Hello everyone, my name is XiaoZiheng. I'm currently a research fellow at Nanyang Technological University, supervised by Professor Tang Yi. And I also serve as a part-time lecturer in the School of Electrical and Electronic Engineering at NTU. Across three MSc level courses, my teaching evaluations consistently rank above school average. My research focuses on power electronics, high-frequency power converters, and AI design, control, and modeling. Over the past several years, I have built a strong track record that bridges fundamental research and experimental systems. I have published multiple first author papers in top-tier journals, received national and international research awards, and served as guest editors for international journals. Importantly, my work goes beyond theory. I actively design, build, and test high-power hardware prototypes, translating analytical models into systems that operate under real engineering constraints. The project I am proposing today, high-efficiency, high-density power conversion for artificial intelligence computing systems, grows naturally from this background, combining deep technical expertise, hands-on prototyping, and system-level thinking. This background positions me well to address a challenge that is becoming increasingly important for the future of AI computing. AI computing drives an unprecedented growth in the electrical demand. Over the next decade, AI-related power consumption is projected nearly by an order of magnitude. At a hardware level, this trend is clearly visible in modern GPUs. Over roughly the same 10-year period, GPU power has increased from 100 volt to 1 kilovolt, as exemplified by the recently released platforms such as NVIDIA's GH200. Notably, this dramatic increase in power did not accompany with a proportional increase in physical size. As a result, today's power delivery solutions, including voltage regulating modules and intermediate bus converters, are increasingly struggle to keep pace. State-of-the-art commercial modules face a fundamental trade-off between efficiency, power delivery, and fast dynamic response. This trade-off creates a critical bottleneck. Without breakthroughs in power conversion technologies, further improvements in AI computing performance will be constrained not by algorithm or silicon, but by power delivery and thermal limits. My research vision is to remove this bottleneck by fundamentally rethinking how high-efficiency, high-density power conversion is designed for AI computing systems. To achieve this, we must go beyond conventional empirical design methodologies. This project introduces three key technical innovations: a reconfigurable system architecture, an optimized power delivery layout, and a data-driven design paradigm. First, the system architecture, the conventional one, has a two-stage from 48 volt to 1 volt, even with very high individual stage efficiencies, for example, 97 and 95. The overall system efficiency is reduced to 98 to 92% due to cumulative conversion losses. In contrast, my approach adopts a direct single-stage conversion, which significantly reduce stage-level losses and enable a higher end-to-end system efficiency. Second, at the power delivery layout, conventional lateral power deliveries place the converters on the same side of the GPUs. This configuration increases the current path length and results in a higher conduction loss. I propose vertical power delivery layout, in which the power converters are placed beneath the processor package, enable a shorter and more uniform current path, and reduce the power delivery loss. Third, at the design methodology level, power converters have traditionally been designed using empirical datasheet-based approaches. Engineers iteratively tune parameters to reach a feasible solution, which is usually far from optimal. In this project, I introduced a data-driven, optimization-oriented design paradigm. By establishing a high accurate efficiency power density Pareto front, the design space can be explored systematically rather than through trial and error method. Using this framework, my preliminary prototypes have achieved efficiency of 98.5%, which is 7% higher than current state of the art, and a power density of 1,800 watt per cubic inch, which is a fourfold improvement over existing solutions. Equally important, this work is supported by strong execution capabilities. I have led and co-led multiple funded research projects across China and Singapore, and coordinated multi-institution collaborations involving universities, research institutes, and industrial partners. I have also co-supervised more than 20 master's students and several undergraduate students, guiding them from theoretically modeling to experimental validation. This experience ensures that the proposed research is not only innovative but also deliverable within the fellowship timeframe. I'm comfortable managing complex projects that involving hardware prototyping, control design, and experimental testing, all of which are essential for the success in this project. AI computing infrastructures are increasingly evolving into converter-dominated physical energy systems. This project naturally bridges the complementary strengths of NTU and KTH. At KTH's Intelligent Sustainable Grid Lab, the research aligns closely with ongoing work on converter-dominated grids, advanced control, optimization, and AI-enabled energy systems. At NTU, this project leverages strong capabilities in high-frequency power converters, hardware control co-design, and large-scale experimental prototyping facilities. Together, these complementary strengths form a unique and highly synergistic ecosystem for advancing next-generation power conversion technologies for AI computing. I have already established contact with Professor Xu, an NTU alumna. We share a strong mutual interest in this research direction at the intersection of AI computing, power electronics, and sustainable energy systems. With the support of the Wallenberg NTU Presidential Postdoctoral Fellowship, I aim to deliver not only high-impact research outcomes, but also to establish a long-term research trajectory that connects AI, power, and energy. Thank you very much for your time and considerations.